Good morning, everyone, and welcome to Ovid Therapeutics, where we are on a journey to pioneer better and gentler medicines for the brain. And one of the ways we're doing that is with what we think is a portfolio of mechanisms for a very exciting target in the brain, KCC2, which stands for potassium chloride cotransporter 2. And while we've had a lot of progress in our epilepsy pipeline, there has also been tremendous progress in our KCC2 portfolio, so we're excited to take you through a deep dive today. I'm Meg Alexander. It's my privilege to be the president and CEO here at Ovid. And I want to remind you we are a public company and we will be making forward-looking statements today. But why we have been so excited to have you here and host you is to tell you more about our vision for KCC2 direct activation. We're pioneering an entirely new class of medicines for the brain and a target that we believe is a master switch for excitation and excitatory-inhibitory balance in the brain. We believe our first molecule, oral molecule, OV4071, is a potential pipeline in a product, and it will be a better, gentler medicine. And we have a very efficient path to proof of concept with what we think are very creative but thoughtful translational biomarker strategies, and we're going to walk you through all of that today. And we believe specifically the opportunity for OV4071, our first oral direct activator, is significant and may serve areas of incredibly unmet need and very large opportunities, which you'll hear about. But I'd like to start by introducing some of the other speakers who will be here with me today. So in addition to myself, we'll be joined by Dr. Oliver Howes. Dr. Howes is the world leader in psychosis, and his lab at King's College of London has looked broadly at the science and translation of psychoses medicines across areas of schizophrenia, neurodegenerative psychoses, etc. And Oliver will talk to us more about restoring excitatory and inhibitory balance in the brain, and specifically how it relates to the indications and the conditions that we're seeking to serve. He'll be followed by Dr. Michael Halassa. Mike is an experimental neuroscientist who has done incredible work in the prefrontal cortex. And what Mike will take you through is not just the relevance of KCC2 for the indications that we're walking into, but Mike has actually used our two clinical stage molecules and tested them in a range of schizophrenia and behavioral models. And he'll share with you that data and start to give you the view of what's giving us conviction here at Ovid. And then finally, I'll be joined by my colleague, Dr. Eliseo Salinas. Eliseo joined us recently. He is a 40-year veteran drug developer. He's got at least 7 medicines to his name, 5 of which are in the CNS, including some of the only medicines in the areas that we'll talk to you about today, therapeutic areas that we'll talk to you about today. But before we get into that, I just want to remind everyone what our focus is here at Ovid. As part of our journey to deliver better, gentler medicines, we are very focused on specifically developing medicines that quell neural excitability. And we're doing that by going after what we think are fundamental targets to that hyperexcitability in the brain, and specifically going after mechanisms of action that are differentiated but potentially universal, that can have broad therapeutic utility. And we're doing this specifically with small molecules because we want medicines that are easy for patients to use. And the result of this focus over the last 5 years has resulted in a very big pipeline that's progressing rapidly in the clinic, so much so that actually for our epilepsy program, half of our team is on the other side of the world launching our phase 2 program and the multiple proof of concept studies that we have for that. But today, we're going to focus on the bottom part of our pipeline, or KCC2, and we're going to take you through a deep dive specifically on the oral molecule OV4071 that was just cleared and that's going into the clinic, but it's moving very fast. And that's important because we believe that KCC2 direct activation can serve therapeutic areas that have tremendous unmet need. While we talk to you a lot about epilepsy because of our epilepsy program, I'd like to direct you to the bottom part of this slide, and specifically some of the indication areas that we think are highly relevant for KCC2 direct activation are not well served today. So schizophrenia, obviously we've known about this for centuries, but in the last 20 years, there's only been 2 novel mechanisms of action, and we know there's trade-offs with the drugs that are available in terms of tolerability. Parkinson's disease psychosis, there's one approved medicine, and that carved an important path. Yet again, it's a medicine that only works for a small subset of the people who have psychosis and PD. And finally, in Lewy body dementia, there's nothing indicated for this form of psychosis. So huge unmet need that we believe we can serve. And why we think we can serve this with KCC2 is we think this target in the brain is almost like a PD-1 moment in neurology. And what I mean by that is, while it's one mechanism, we believe it can potentially be many medicines for the molecule we're talking about today and the subsequent development candidates that we'll have coming out of this portfolio. And why that is really unique to this particular target of KCC2. So KCC2 is a common master switch that helps regulate neural excitatory inhibitory balance, something that Oliver is going to talk to you much more about in a couple minutes. But why KCC2 is so unique is it's expressed exclusively in the CNS, unlike other ion transporters. It very precisely helps regulate and rebalance neural network hyperexcitability. And its geography matters. And what I mean by that is it sits upstream of many of the approved medicines for things like schizophrenia, like the dopamine D2 antagonists, but it sits downstream from many of the genetic or acquired causes of hyperexcitability. So it's in a perfect location to be able to serve a number of different conditions and relative to existing therapeutics. Importantly, it only works when this transporter is suboptimally extruding certain ions, specifically chloride. And because of where it sits, it converges in the broad spectrum of both disorders and symptoms that are driven by neural hyperexcitability. And finally, what's so exciting about KCC2, you can't overmodulate this target. And that's different than a lot of the medicines we've historically seen in the brain, where when you operate on neurotransmitters, you can overdo it or underdo it. But KCC2 does not allow energetically for you to extrude too much chloride, which is one of the main ways it functions, so it's hard to overmodulate, making it very attractive. And put simply, when you look at the mechanism of action of KCC2, essentially, when this transporter is dysregulated, it's not balancing potassium and chloride. Why that matters is when the neuron doesn't extrude the appropriate amount of chloride, GABA, the main braking system in our brain, cannot operate in an inhibitory fashion. Putting it really simply, it means the braking system in our brains can't work. But when you directly activate KCC2, and keep in mind I'm going to keep talking about direct activation, that matters, you're able to, and we are able to extrude the appropriate amount of chloride. That allows GABA to be hyperpolarizing, the brakes in our brain are restored. And therapeutically, this is a big deal. If you look at literature alone, you can see that the opportunity of potentially directly activating KCC2 could be enormous, from addressing neurodegenerative forms of psychoses and cognition, to anxiety and behavioral dysregulation, to pain, trauma, neurodevelopmental conditions, even seizures and epilepsies. The opportunity, again, is very large here. One mechanism, many potential medicines. But frankly, I wouldn't be convinced by the literature alone. What convinces us is evidence and data. So what you're going to see from us today is a broad armamentarium of data that we have been amassing for our clinical KCC2 direct activators. Now, I recognize the table on the right is a bit of an eye chart, and we're happy to go through this with you in detail today. But essentially what you are looking at is a snippet of some of the pharmacodynamic disease biology models that we have run with our clinical direct activators of KCC2. And you can see we've run these across psychosis and anxiety and seizures and pain. And I will be the first to say up front, I don't trust an individual psych model in an animal. It's not the same thing as what we experience with someone who may be living with schizophrenia, for example, and the full panoply of symptoms that they experience. What we do trust, though, and as part of our translational strategy, what we have done is we have looked at the best models, both genetic as well as perturbant models, stimulant models, to be able to look at what is the underlying biology happening in these models, and being able to trial our KCC2 direct activators to see, are we restoring that EI balance? And indeed we are. Now across more than 25 different pharmacodynamic models, we have been able to show consistently that our clinical stage direct activators are restoring EI balance. They're doing so in a way that's consistent with the mechanism of action of KCC2. And also what gives us incredible conviction, which you're going to hear about from both Mike and Eliseo in a couple minutes, is we are also running our medicines against reference products, so known effective drugs, including older ones and some of the more recent ones. And we're seeing activity that's not only consistent, but in some case surpasses the medicines that we have available today. So in totality, this armamentarium is giving us great conviction and a lot of excitement to advance this rapidly in the clinic. So I'm going to hand it over to Oliver Howes in a moment, who's going to talk about the role of EI balance in the brain and for these indications. And then we'll continue to tell you more about our translational strategy and the data that gives us confidence. Oliver?
Thank you. So I've been working in neuropsychiatry for over 25 years, both as a clinician and a researcher. And I want to tell you why I think this KCC2 target is one of the most exciting that we've seen for a long time. And to do that, I've got to talk you through a bit of the biology, the neurobiology of psychotic disorders like schizophrenia. So the brain is a bit like a computer in that it uses electrical impulses to transmit and process information. And this relies critically on the balance between excitation and inhibition in the brain. And on this slide in the middle circle, you can see the main inhibitory nerve cells in the brain, the ones labeled GABA, and then the main excitatory ones, the ones labeled glutamate. Now these make up the vast majority of the inhibitory and excitatory nerve cells in the brain, and they're critical for this excitation-inhibition balance. Multiple lines of evidence now show us that psychotic disorders like schizophrenia, there is an imbalance in these nerve cells. And we think that this leads to a glutamate-driven excitation in the prefrontal and other cortical regions, which then, through that projections down to the midbrain, shown in red on the brain figure, lead to overexcitation of dopamine in the midbrain that projects up to the striatum. So it leads to surges in striatal dopamine. And this, collectively, explains both the positive or psychotic symptoms, but also the other cognitive and other symptoms that we see in disorders like schizophrenia. Now, as I said, there's multiple lines of evidence supporting this that have accrued over the last decade or so. I've summarized some of them on the left, starting with the genetics and epigenetics, where we've now had these really massive studies with tens of thousands of patients in them that have shown genome-wide significance for excitatory pathways being implicated in the disorder. So that gives me great confidence that there's something to do with excitation-inhibition imbalance in the disorder. But on top of that, we've also got post-mortem data, which has shown repeatedly that there are lower levels and loss of inhibitory GABAergic markers in cortex in people with schizophrenia, particularly in the prefrontal cortex. And then we've also got consistent evidence from imaging on a variety of techniques, EEG, fMRI, PET, that all indicates that there is EI imbalance in the disorder. So this is converging evidence from multiple different streams of evidence for this cortical EI imbalance that could lead to all aspects of the syndrome. Now I want to drill down onto the EEG in particular, because I think this is really interesting as a marker, because as I said, the brain is working through electrical impulses, and electrophysiology, like EEG techniques, these techniques are measuring electricity. You can see that on the left. You see the skull cap with the electrodes. This is what we use to measure the electrical activity of the nerve cells. And below that you can see actual recordings in people when they're doing one of the tasks that you'll hear more about later on, the ASSR task. So you're actually measuring in real time this function of the brain. On the right, what you can see is measurement of this electrical activity in people with first episode psychosis compared to healthy controls. And the first episode people the data are in blue. And what you're seeing is the level of high frequency activity, this gamma band activity. So this is from 30 hertz up. Now this is particularly dependent on these GABAergic cells that sculpt the interaction between the EI balance. And you can see that you've got overactivity in this resting gamma in first episode patients. We don't just see it in the first episode though. Studies have also been done in chronic schizophrenia and even in the prodrome. And you get this repeated pattern across these studies indicating this EI imbalance. Now I also want to show you some work that we have done that have tested whether this leads to the striatal dopamine changes. So here this was a study in mice where we used ketamine. This is an NMDA antagonist. You'll hear more about this model later, but it disrupts EI balance. And you can see on the left that when you give this repeatedly to mice, then wash them out, you get this lasting reduction in inhibitory GABAergic cell markers in the cortex of these mice. So this is reproducing what we see post-mortem in schizophrenia. But on the right you see but this also leads to the same striatal dopamine changes that we see in psychotic disorders like schizophrenia. So the ketamine-treated mice in red showed higher striatal dopamine activity measured with PET, which is the same technique that we use in patients and have shown that patients have higher dopamine in the striatum, and that is associated with the severity of their psychotic symptoms. So this is consistent with this model that EI imbalance in the cortex is leading to this upregulation of striatal dopamine and the psychotic symptoms. So how does this lead to something that might target the unmet need in schizophrenia? Well, on the left you can see this circuit diagram and the prefrontal cortical EI imbalance. The prefrontal cortex is really important for motivated behavior. So this is having motivation to go out and do your tasks, interact with people, get a job, work, etc., etc. If this is impaired, you can see how this might lead to the negative symptoms of schizophrenia. So these are symptoms like loss of motivation and social withdrawal, which are amongst the most disabling symptoms of the disorder. Prefrontal cortex is also important for planning and working memory, and you can see how this would impair cognitive functions, so lead to cognitive impairments. And on the right you can see that these are major unmet therapeutic needs in schizophrenia and other psychotic disorders. We have no treatments that are licensed for them. They're seen in about 2/3 of patients with schizophrenia, and they are amongst the main predictors of long-term outcome. You can imagine if you've got no motivation to get on with life, you're not able to get a job, you don't have a family, etc. And underneath you can see the psychosis angle. Now, of course, we have D2 blockers for psychosis, but these are ineffective in a large proportion, about 1 in 3 patients, and have lots of safety liabilities and side effects, which are listed there. And then we've got drugs like xanomeline and trospium combination, which you'll hear a bit more about later. This is effective for psychosis, but again, probably not in everyone, and is also limited by poor GI tolerability. So there's an unmet need here for a treatment that will also address psychosis as well as these other aspects of the syndrome. And you can see where the KCC2 activation might work for this, because by targeting this GABA dysfunction, it could help restore EI balance, reduce the negative symptoms, restore cognitive function, and potentially also reduce the psychotic symptoms as well. So this is the potential to target the whole syndrome. That excites me. But it also is relevant to other psychotic disorders where we also see this EI imbalance. So one that I also want to highlight is Parkinson's disease psychosis. So you get psychosis in about 40% of people with Parkinson's disease. You also see it in people with Lewy body dementia. And here you get EI imbalance across the cortex, and you can see some of the regions highlighted in that pink color on the brain on the right. And one area where you've got particular reductions in GABA is the visual cortex. And this may explain why you get a lot of visual hallucinations in Parkinson's psychosis. These occur in about 28% of people with Parkinson's disease. And you can also see how this might disrupt cognitive function and cause delusions as well through disruptions in EI imbalance in other regions. Now, in terms of treatments for Parkinson's disease psychosis, we have treatments like clozapine, which are not licensed and have major metabolic issues. And believe me, I've used this to try and treat Parkinson's psychosis. It is really hard to use. It's hard to use in schizophrenia, but even harder in people with Parkinson's disease because they're even more sensitive to the side effects. And then we've got pimavanserin, which is licensed but has limited efficacy and also has side effects as well. So there's major unmet needs here. And again, you can see where KCC2 activation might help, because again, by targeting the upstream pathophysiology, this EI imbalance, it could help address both the delusions and hallucinations that we see in the disorder. So I hope I've set the scene for you. I'm now going to hand over to Mike, who's going to give you more direct evidence about KCC2.
Thank you, Oliver. Good morning. So I wear 2 hats. I'm a psychiatrist. I see patients almost exclusively with psychotic disorders, schizophrenia. And I also run a lab that goes after the mechanisms, the fundamental mechanisms of cognition, how neural circuits give rise to all the mental faculties that we have. And that allows us to reverse engineer many of the functions that we're interested in and that are perturbed in schizophrenia. Now, schizophrenia clinically is a devastating illness. Parents see their kids growing up through teenage years with all the promise in the world. They hit 18, they have their first break, and it's a downward slope for many of them. They never recover function, don't have jobs, and never, do the normal things that every adult aspires to do. So what do we do about that? And the fundamental problem is, what Oliver was talking about, is the loss of frontal function. We have medications to quiet the voices, but we have very little in the way of restoring their functional capacity. Well, one of the clues to what may be perturbed, in addition to the loss of GABAergic neural activity, is the loss of KCC2 itself, the molecule that we're talking about today. Multiple post-mortem studies in schizophrenia suggest that there is an actual reduction in KCC2 expression in the prefrontal cortex. How can we start asking questions about what that does to frontal function and cognition? Well, that's why we use animal models. So my lab specializes in the ability to reverse engineer these deficits using animal models. So on the top part of this slide, what you're seeing is our ability to go into the frontal cortex and ask, does KCC2 levels also change in models that are relevant to schizophrenia? And here I'm showing you two different models. A genetic model called the 22q11 deletion syndrome. In humans, the genetic change increases schizophrenia risk by 25-fold. The other one is chronic methamphetamine use. It is well known that chronic methamphetamine use in humans gives you a syndrome that you cannot distinguish from schizophrenia proper. So that's the top part of the slide. The bottom panel is electrophysiological readout of KCC2 activity. It's indirect in prefrontal neurons. So this is the application of GABA, and as Meg was talking about, GABA looks hyperpolarizing in the black trace, but in these two different schizophrenia models, it becomes more depolarizing, meaning that it doesn't work the same way in these two models. So now we have expression is reduced, function is reduced at the single neuron level in two models relevant to schizophrenia. Does that impact information processing in ways that we can measure? And the answer is yes. One of the things that we do in the lab is direct readout of electrical activity, population electrical activity in the prefrontal cortex. The setup is all the way on the left. We do multi-electrode recordings, measure activity for multiple neurons at the same time, and use a technique called optogenetics where we activate populations of neurons using light. And in the middle panel, I'm showing you the actual readout of this technique. The top part of that panel is what normal prefrontal activity in response to exogenous stimulation looks like. Each of these blue ticks is optical stimulation of a subpopulation of cortical neurons, and the black trace is the population response of their neighbors. So what you see is excitation followed by very sharp inhibition. That's the EI balance that we've been talking about. That's exactly what the readout looks like. If you look at the bottom panel, that is the 22q11 deletion model. What you basically see is that you get excitation, but the inhibition looks pretty wimpy. So and what accumulates in between these pulses is what we call neural noise. So the traces are a lot more noisy, reflecting the type of noise that may accumulate in actual cognitive tasks. On the right-hand side is a direct quantification of that, summary statistic, and again, you see wild type or control maintains a high signal-to-noise ratio, which you can see, and the 22q11 has a lower signal-to-noise ratio. We see the exact same thing in the chronic methamphetamine model. I'm just not showing it for the sake of time. Okay, how does that impact behavior? Are we able to read this out in prefrontal relevant behaviors? And the answer is yes. So in the lab, we've developed a variety of tasks to be able to directly evaluate prefrontal function. Those tasks are, we give animals instructions, and we then ask them to allocate their attention to categorize different objects. And what we basically are able to do is tax the prefrontal function using two different manipulations that I'm showing you on this slide. We change the delay between the instruction that we give the animal and the categories that they present. We do that parametrically. So it's akin to giving somebody a phone number to remember and then waiting for different periods of time to ask them what that was. So that the longer you wait, the harder it is. And then the second is task switching. We can switch the instructions that we give them, and you can see, this is on the right-hand side, their performance drops after the switch, and it takes a few trials to recover. It's similar to if you play video games. You can play game 1, and then you switch to game 2, and if you're not very careful, you might be playing game 1 still, so you make a lot of mistakes until you realize, okay, this is a different game. So that's what happens to mice in this assay. Now, this is a substrate upon which we can evaluate directly schizophrenia-relevant changes in prefrontal function. And across these two different models, we see deficits, both in working memory, 22q11 on the left-hand side, red traces, and in the chronic methamphetamine model, orange trace on the right. And that becomes the substrate by which we can evaluate schizophrenia-relevant medication, including Ovid novel compounds. Okay, so now if we look in the 22q11 model and ask, what do commercially available antipsychotics do for our prefrontal readouts? And the answer is nothing. So if you look all the way to the left, we use risperidone, a traditional D2 antipsychotic. It does nothing for working memory or task switching. Xanomeline trospium, Cobenfy, which is a first-in-class muscarinic agent, in this particular model doesn't seem to have any efficacy on any of these readouts. But if you look at the Ovid KCC2 direct activation, it improves both working memory and task switching in this 22q11 model. What happens to the chronic methamphetamine? Again, risperidone does nothing. Cobenfy improves task switching. So in one of 4 conditions, Cobenfy seems to be doing something that's consistent with what has been published in clinical trials on its pro-cognitive effect. So we can read that out. But if now you look at the KCC2 direct activation, it restores both working memory and does improve task switching. So, and this is, okay, sorry. So what I just showed you is basically across 2 different schizophrenia-relevant models where we've measured physiology, where we've measured behavioral readouts. KCC2 direct activation improves working memory and task switching and outperforms existing and commercially available antipsychotics in these particular readouts. So to summarize, and as my colleagues mentioned, excitatory inhibitory balance is disrupted in the schizophrenia prefrontal cortex, and I want to emphasize that what we're treating in clinical psychiatry are many of the downstream consequences of that kind of initial blast. Reduced KCC2 function may be an underlying mechanism. That's why we do animal work at all, because we can't really do these direct measurements of KCC2 function in the human brain, so we use appropriate animal models. KCC2 activators have utility across genetic and pharmacological models related to schizophrenia. And KCC2 activation has broad symptom targeting beyond positive symptoms, including cognitive function, which is correlated with negative symptoms. And now I hand it off to Dr. Salinas.
Thank you, Michael. Good morning. Happy to be here to talk about how we plan to study 4071 in the clinic. As Meg mentioned, I've been for a long time doing drug development. In fact, I was telling Oliver that the first study I wrote, a protocol 38 years ago, was the first amisulpride placebo-controlled trial. And as you know, LB Pharma now has been successful with a new version, the son of amisulpride. But unfortunately, not much has changed since then. Not much has changed since then, as Meg said. This is what brought me to help Ovid. 4071 is a direct KCC2 activator. It's important, the word direct. It has a broad potential in the psychotic syndrome. That means that it applies to psychotic aspects in different disorders, schizophrenia, Parkinson's disease psychosis, and so on and so forth, including to Alzheimer's psychosis, which is a very big indication. We have a lot of data, convergent data, rescuing signs of positive symptoms and negative symptoms in animal models of psychosis with commensurate or superior activity when compared to established antipsychotics like xanomeline or pimavanserin. Importantly, no sedation. You don't want to have the psychotic patients sedated, in particular the elderly. We have seen no sedation or catalepsy. And finally, as you have heard from Michael and Oliver, something very important in drug development, which is a biomarker, a translatable electrophysiological marker connecting pharmacology and behavior. The fundamentals are here. Potent and selective KCC2 direct activator with an ED or EC50 of 0.6 micromolar, suitable for chronic dosing, clear bind and activation demonstrated preclinically, very nice therapeutic index. We can go very high on doses without problems. No sedation, no anticipated significant drug-drug interactions, and a good brain penetration, which is essential for the CNS active drug. This is a busy slide I will let you read after the presentation, but essentially what it talks about is the convergence of data. As Meg mentioned, we are not dependent on a single model to determine the value of this compound. We're not convergent. And you have here summarized 4 different models, MK801 and amphetamine, hyperlocomotion. This is important. I'm not going to describe them later, that measure what is called positive symptoms, hyperlocomotion in the case of animals. The middle one is social interaction, a different construct that only achieved with chronic dosing of PCP. And finally, a genetic model of Rett syndrome, which is not schizophrenia, but shares some of the aspects that we are talking about. So, getting into the data now. This first slide describes the results in the MK801 induced hyperlocomotion. This is a single dose model. You give MK801 to animals, and the animals behave like crazy 30 minutes later. You see in the graph on the left, before, so you pre-treat the animals with the testing compounds, in this case, OV4071 at different doses, starting at 0.3 milligram up to 60 milligram. And you see their baseline activity before you give the MK801 injection. Then with the MK801, you see an explosion in ambulation in those animals, which is reduced by OV4071, started at the 3 mg per kg dose. Please remember that dose because we're going to see it consistently. On the right-hand side, you see the dose effect curve, which allow us to estimate the expected ED50, which is 1.6 mg per kg. So we have an idea of what are the doses that might be effective in humans. A different aspect in the same model is represented in this graph. As I mentioned, you give MK801 30 minutes before measuring activity, but you pre-treat the animals with the target compound. And the question is, how long should you pre-treat those animals for? A day, 2 days, 3 days? And this graph represents, so in some animals were pre-treated with Ovid 4071 for 7 days. Some animals were pre-treated for 5 days, others for 3 days, and one group of animals received one single dose of Ovid 4071 30 minutes before the injection of MK801. And what we see in the graph, and you have in the order of the activity, how much they're moving around, the strongest effect is produced by the single dose. That's testament to the efficacy and the potency of the drug to alter the behavior with one single dose. Importantly, you don't lose efficacy upon repeated administration. So you don't see tachyphylaxis. So this was very important, a very important behavioral readout for us. On the right-hand side, what I said before, it is brain penetrant. You see the concentrations, which are equivalent between the single dose and the 7 dose, no significant accumulation. Now, same construct, hyperlocomotion, but a different challenge with amphetamine. Why is that important? MK801 is an NMDA antagonist, like ketamine, like PCP. Okay, produce a glutamate burst in the cortex and increase in dopamine in the striatum. Amphetamine directly increases dopamine in the striatum directly. Why is this relevant? Well, typical antipsychotics are effective on both MK801 and amphetamine-induced hyperlocomotion. Pimavanserin is effective on the MK801. It's not effective in the amphetamine model. And this is in the public domain. You can search the publication and you'll find it. So, same construct, different mechanism of action, same effects. Quickly, on the left-hand side, you have, like in the previous slide, the animals, before they were treated with the comparator, with the active drug, before they received the challenge with amphetamine. And you see in the gray bar on the left that that's the normal ambulation of mice in the open box. So about 4,000 inches moving around over a period of time. When you give him haloperidol, Aldol, a typical, very effective dopamine 2 blocker, you see what happened with the spontaneous ambulation of these animals. That's why patients, families, and treating psychiatrists, as I was before getting into industry, we call those straitjacket drugs. Because if you take Aldol, everybody's going to see that you are on Aldol. They stop moving. With Ovid 4071, you don't see that much of an effect on spontaneous ambulation. Okay? But then when you give the challenge with amphetamines, you see a significant increase in the ambulation, and you see on the gray bar animals going from 4,000 inches to 8,000 inches. That's the hyperlocomotion. Aldol, again, suppressing everything. And Ovid 4071 being statistically significantly effective, but if you compare the bars on the right with the bars on the left, you see that roughly the Ovid 4071 treated animals under amphetamine challenge have similar levels of ambulation as they had before receiving the amphetamine. And again, previous models, minimal effective dose, 3 mg per kg. Different model, 3 mg per kg is effective. Finally, as Michael mentioned, psychosis is not, or in other words, it's not only about hallucinations, delusions, and agitation. It's about these negative symptoms that are the most challenging to control. One aspect, Michael showed about cognition and how these direct activators affect cognition. This is another aspect, social interaction. This model measures how much rats interact with each other. And in order to produce a deficit on social interaction in rats, a single dose of PCP or MK801 is not enough. You need to pre-treat the animals at least for 5 days. And that testament of the different mechanism of the challenge. So probably producing a cortical deficit that Michael was talking about that is at the origin of this decreased social interaction. What we see in the graph is that comparing the black bar with the gray bar, you see a significant decrease in social interaction. Next, on the red bar, corrected by clozapine. Not the perfect antipsychotic, but one of those that we consider that still a dopaminergic blocker, but having pretty good efficacy. And you see similar efficacy of OV4071 again, starting at 3 mg per kg. And all this is oral. I mean, the 3 moles I mentioned is oral doses. So, of course, we don't hang our hat in a model. But the convergence of data is what gives us confidence that we are targeting here something that is relevant for the disorder. Now, both Oliver and Michael were talking a lot about electrophysiology. Electrophysiology is the connection between the pharmacology and behavior. And we spend a lot of energy assessing the electrophysiological profile of these drugs. What we have here is quantitative EEG. That's different from the EEG we look at to see if a patient has seizures. Quantitative EEG measures the fraction of delta, theta, alpha, beta, or gamma frequencies in the EEG. And what we have here is the model of Rett syndrome I mentioned earlier. You have in white the frequencies, the power of the animals before treatment with 4071, and in purple after treatment with 4071 at 1, 2, and 3 hours. And what we see is a decrease in gamma frequencies in the animals treated with 4071. The same gamma frequencies that Oliver was mentioning are increased in first episode schizophrenic. The same gamma frequencies that get increased when you give ketamine to healthy people. We see also an increase in delta frequencies, which might be suggestive of an effect on synaptic strengthening, and we can discuss that later. Another way to look at electrophysiology is the following. Now, we have a lot about the KCC2 channel and GABA, and then some sort of reasonable person would say, well, give them more GABA. Why don't you give them more GABA? And this is what happened when giving GABA, which is benzodiazepines, for example, are excellent GABA activators. They work very well in a lot of things, not in schizophrenia. What we have here is the results with OV350 and OV4071, two KCC2 direct activators. And you see the darker curve represent post-treatment and the lighter curve before giving the drug. And what we see is that the two drugs do essentially the same. They suppress gamma frequencies. From 30 hertz onwards, you see a shift downwards. Then we have on the extreme right, zuranolone, the Sage compound. So we try to compare head-to-head, same type of animals, same lab, what a GABA activator does. And that's exactly what benzodiazepines do. What do? They increase beta frequencies. That's the typical effect of benzodiazepines in the QEEG. So it's not only about GABA. So it's a way of making existing GABA more effective. If you have a defective KCC2 channel, probably all the GABA of this world is not going to help that much. Finally, these are results of the ketamine challenge in mice. Why ketamine? Because it's an NMDA blocker. It produces the same effect in animals as we saw with MK-801. And we're going to be doing, as Meg is going to tell you, a ketamine challenge in humans. What we have here, these are different doses of 350, one of our direct activators. And what you have here is all the frequencies. First, the total power. Does it go up? Does it go down? With benzodiazepines, total power goes down. There's a decrease in total power. You don't have that with OV4071. And then you have the different frequency bands from delta to gamma, and the horizontal line represents the effect of ketamine. So if above is more than ketamine, below is less than ketamine. And what we see here is exactly what we expected, mostly a decrease in gamma frequencies, statistically significant at the 3 dose level. You also see this increase that doesn't reach statistical significance on the slow frequency bands, and I'm really looking forward to seeing the data from our human studies looking at those. To summarize, we have seen data with robust results indicating activities in different aspects of the psychotic syndrome in different animal models. We have seen that 4071 is potent and effective at single and repeated doses. We have data showing that the decrease in striatal dopamine consistent with what we have seen in behavior. Importantly, with this biomarker that will enable us to track how the drug is performing in the clinic, and finally with strong brain penetration and no sedation. And with that, I'm going to hand it over to Megan.
Thank you, Eliseo. And I will talk a little bit more about our translational clinical strategy. But just to recap, Oliver has told us about the role of EI imbalance in a number of different forms of psychoses. Mike has told us about specifically the role of KCC2 expression and EI imbalance related to the indications we're interested in for OV4071. And he's shown with our direct activators that he's actually able to restore dysregulation of KCC2 and in doing so rescue cognition and more normalized behaviors and working task memory. And now what we've shown you, we get it's a lot of animal data, but what it's doing systematically is confirming the underlying disease biology that our KCC2 direct activators are moving the neurotransmitters as they should, that is highly relevant for the underlying disease process that's driving some of the worst symptoms across a range of psychoses. And all of this together is giving us incredible excitement and conviction to get our direct activators now into patients. And with OV4071, we believe that the opportunity is very large. Specifically, we see it as a broad syndromic psychosis medicine and also relevant for other psychiatric disorders. And the picture behind me gives you a sense of where we think OV4071 has therapeutic utility. Now, don't worry, we're not going to try to prosecute all of these at the same time in the clinic, but what you will hear us say today is in addition to our original interest in PD psychosis and psychosis associated with Lewy body dementia, we will also be initiating a phase 2 proof of concept study in schizophrenia next year if our clinical translation plans go as we expect that they will based on our totality of data behind the program. And let's talk a minute about the translational strategy, because we've talked a lot about neurotransmission in animals relative to genetic and stimulant-induced versions of psychoses. But essentially our strategy has been this, because we are sensitive to the challenge of developing in psychiatric indications. Many smart companies and researchers have come before us. So as you can see, what we have been looking to do is really assess the underlying biology and pharmacodynamic activity of our direct activators, including OV4071, both in phenotypic screens but also in disease models. And we're looking at this in a variety of ways, right? Both genetic models of these diseases, induced models, and we're doing it against reference drug comparators, and we're using electrophysiology, so we're not looking at behavior alone. What that is now enabling us to do is to take biomarkers like quantitative EEG, but frankly many more, into our healthy volunteer study. Of course, we need to step through the right drug development steps of safety and tolerability assessments. But while we do this, much like we handled with our epilepsy program, we will cast a broad net characterizing the electrophysiology based on all of these robust insights that we've now gotten from these disease biology models. Similarly, we will be running a ketamine challenge study, as Eliseo alluded to. Why does that matter strategically? As Eliseo has said, ketamine is an NMDA antagonist. So what it does is it directly reproduces the same biological and neurotransmitter surges of glutamate and dopamine in a healthy volunteer. And we can assess against quantitative EEG some of these same biomarkers and others if we're able to shift the neurotransmission function back in the right direction. What does that enable us to do? It enables us to make smart and hopefully confirmatory decisions about how we're able to modulate the biology that's underpinning some of the worst symptoms of psychosis. And it allows us to make smart decisions about indication sequencing. And then finally, of course, we're trying to move rapidly into patient proof of concept studies because we believe the opportunity with OV4071 is broad. We think this is, as I said before, essentially a pipeline and a product unto itself. But it's not just animal data that we're resting on. I recognize we've given you a lot of animal data here today that's giving us conviction, but we also have human data. So many of you recall, we had a tool program that we read out at the end of last year. It was an intravenous direct activator of KCC2. That program name was OV350. LSAO alluded to it a couple times in some of our earlier animal models. We spoke to you at the time mostly about safety and tolerability. We were excited to show that we can safely drug this class. But what we didn't spend as much time talking about is that we also saw suggestion exactly of the same kind of biomarker signals that now we've shown you over and over and over again in animal models. And what I mean by that is on quantitative EEG, so same types of biomarkers that LSAO was just mentioning a moment ago, we were able to see central activity that was consistent with a spectral power shift, so consistent with the KCC2 mechanism of action, and we saw gamma band changes specifically in that phase 1 study in healthy humans. And that was aligned with when we knew we had drug exposure in the brain. So encouraging that all the disease biology that we've seen in animals, we've also seen start to play out in a very focused human study with our tool program. So that's giving us the conviction to walk into our phase 1 program. In many ways, this is a traditional phase 1. There's a couple things I'll call out about it. One, you can see we've got a number of cohorts. The reason why that is we think we have a drug that's going to be highly effective based on low doses, as LSAO had mentioned, and we have very good safety margins, so we may have superb tolerability. We will fully characterize the opportunity here because we think it could be very broad. In addition to that, you'll see we have an elderly cohort because we have conviction that this could potentially be a very good future drug for various forms of neurodegenerative psychoses. And then finally, you see that we will also have the ketamine challenge, and we'll initiate that once we have our PK well characterized and our Cmax well characterized. It's important from a design perspective. So what that means is the next 12 to 18 months is going to be very busy for our team here at Ovid. We're initiating that phase 1 this quarter. We've been cleared, as many of you know. The ketamine challenge we intend to start in the second half of this year, based on what I said a moment ago. And then in the middle of next year, we intend to initiate, or basically near the end of H1, we intend to initiate a true schizophrenia phase 2 proof of concept study. Concurrent to that, we will initiate a safety and signal finding study in Parkinson's disease psychosis and psychosis associated with Lewy body dementia. And you can see on the far right-hand column here some of the primary endpoints that we'll be exploring in those studies. But a big piece of our strategy to de-risk our asset is very similar to the type of strategy that we took with 329. We try to ask the important questions early to learn as much as possible and elucidate as much as possible the pharmacodynamic attributes of our molecules to be able to best develop them. And a big piece of that is using a biomarker strategy. Now, I will say we are conducting a very broad array of biomarkers, both in our phase 1, where we'll use electrophysiology in healthy humans, as well as in the ketamine challenge study. We don't have time. It'd be a whole day lecture with our guests to be able to talk about all the biomarkers and their applications for each of the conditions that we may want to eventually explore for KCC2. But I'll direct you to a few of them here. First, you've heard us talk a lot about quantitative EEG. That allows us broadly to assess arousal and activation. Things like mismatched negativity allow us to look at essentially the change in detection in a sensory scene. The auditory steady state response gives us a sense about neural synchrony and where you may not have synchrony. Pre-pulse inhibition is another biomarker that we use that helps us assess essentially auditory sensory gating. And we're using both EEG, so electroencephalography, as well as event-related potentials to help us explore these broadly. But what does that mean in terms of the indications we're talking to you about? Each of these biomarkers has different signatures, as you heard LSAO start to describe, in different conditions. And we'll give you an example here, but there are many, because obviously we're looking very broadly, much as we did with our epilepsy program. So, for example, in a population of people living with schizophrenia, there has been good data showing quantitative EEG has a signature of how certain neurotransmitters drive frequencies. So, for example, in someone who's living with schizophrenia at resting state, they tend to have essentially lower that slow wave motion, so delta, for example, and theta. and higher frequency of gamma. You heard LSAO expound on that earlier. So by giving our direct activator in something like a ketamine challenge, if we're able to reverse that, right, just as LSAO showed that we have in animals where we increase delta power and we decrease gamma, that gives us a good sign that we're operating on the neurotransmitters in a way that we can see through quantitative electrophysiology that may be beneficial to the symptoms of the disease based on what we know. And the same is true if we look at Parkinson's disease psychosis. In this one, I'll point you to a different biomarker, mismatched negativity. So we're casting a broad net, but these have read-through for many different forms of psychoses. And this helps us learn a lot, again, early, to make the best decisions for the clinical trials that we walk into. So in mismatched negativity, for people who have hallucinations associated with Parkinson's disease, this particular biomarker, their visual, specifically mismatched negativity, is particularly reduced. So if we're able to show in a ketamine challenge that, again, we're able to modulate this in the opposite direction, what does that give us? It gives us more conviction that the drug is acting as it should and potentially helping with what could be pharmacodynamically beneficial attributes for the indications we're walking into. And I think it's important, sometimes we get a lot of questions when we talk about a ketamine study. I think rationally you all are hearing it's a very similar perturbant to what we used in animal models. It's an NMDA antagonist. So we can reproduce some of the underlying disease biology and neurotransmission that we see happening in disease. But in the past, other drug developers have sometimes tried to use ketamine challenges to change behavior, right? And what we see as the true advantage of the ketamine challenge is to look at electrophysiology, to look at the activity of neurotransmission in the brain and allow us to confirm that we're seeing the changes that we want to see that should be supportive of symptom relief in these indications. And this gives you a sense of what the protocol for the ketamine challenge will look like. So it will be a true crossover study. The subjects will be healthy volunteers, but they act as their own natural controls. And on the right gives you a sense of some of the electrophysiological biomarkers that we'll be assessing. So we'll be looking at, quantitative EEG, as we mentioned before, event-related potentials. Some of those biomarkers I mentioned just a moment ago are the exact same ones that we'll be looking at, in addition to cognitive testing, which we will also do a battery of series that are well characterized, as well as plasma-based biomarkers. So we expect to reap a lot out of this, and we'll be reading it out around the end of this year. What does that mean to where we go next? Well, we want to get to patients as rapidly as possible. I mentioned we'll be conducting a true phase 2 proof of concept study in schizophrenia. We expect that to be a multi-site study here in the U.S., and we'll be looking specifically at acute schizophrenia. While we believe the opportunity is broad, we're going to be focused in this initial phase 2 in terms of the various symptoms of schizophrenia that we can operate on. Simultaneously, we'll be launching a phase 1B exploratory signal finding and safety study, as I mentioned, in PD psychosis, as well as Lewy body dementia psychosis. And we'll be looking at safety tolerability, but again, we'll use electrophysiology to help us establish a signal. And if we do this the right way, we think this will not only create an entirely new class of medicines that could be deeply meaningful in indications that have very few or unfortunately very limited therapeutic options, and if we do this right from a commercial perspective, we think the commercial opportunity could be quite vast. If you look at the 3 indications alone that we've talked about today, and not some of the other ones that could also be relevant, like Alzheimer's psychosis, this is more than a $6 billion opportunity unto itself. But most importantly, we think this is a potential drug that could really help so many patients who don't have good options. So in sum, what that means is the next 2 years at Ovid are going to be very busy. Between our epilepsy program, where our colleagues, half of our team, our CMO and CSO, are on the other side of the world launching all of our phase 2 proof of concept studies, and this KCC2 portfolio, we have somewhere between 5 to 6 proof of concept studies reading out over the next 6, 12, 18, and 24 months. So it's a big year of execution, but we're very excited about the patient populations that we may be able to help. And just in summation, hopefully you've learned a little bit more about KCC2 today and all of the disease biology, pharmacodynamic data, tolerability data that's giving us conviction about the type of medicine that 4071 may be. And we truly believe that directly activating KCC2 is one mechanism with infinite possibilities. We believe we have a very good molecule to take into the clinic. We think the translational biomarker strategy and the electrophysiology we are undertaking will help us ask and answer many important questions about potential indications we walk into. And we are the company that will pioneer KCC2. And if our bet is right on this, we have an entire portfolio of additional next generation development candidates underneath of this so that we can truly unlock the full potential of KCC2 direct activation. So with that, I want to thank you for your attention, and we'll now open the floor for Q&A along with our experts. I saw Laura's hand up first, and we'll start with individuals in the room, and then we'll take any of our participants who are online. Sorry, we'll get you next, Laura. It looks like the mic's up front. Ritu.
Thank you. Is this working? Okay, great. Hi, everyone. Ritu Baral from TD Cowen. Thanks for taking the question. I guess the first question... Ritu Baral, TD Cowen. The first question, Meg, is as you look at the different types of conditions you're going after and the phase 2 studies, one, do you anticipate the primary endpoint will be sort of the more classic psychosis endpoints of like the SAPS and the scales used for PDP? And then second, as you think of the aspects of not just the hallucinations, but also the cognitive impairment of the different indications, they seem to be very different. With schizophrenia, you have the visual hallucinations, the auditory hallucinations, and you mentioned that the cognitive impairment was more sort of task switching and working memory versus PDP, LSA. You and I talked about this way back in Acadia, where it was more visual hallucinations and like executive function. So how does like the mechanism fit into those sort of different profiles?
So endpoints is the first question, and then the second one was the broad symptoms and where we act, right?
Yeah, great to see you, Ritu. So yeah, great question. At the symptom level, as you said, the most prominent hallucinations in schizophrenia are auditory. The most prominent hallucinations in PDP are visual. The field believes that this is due to the areas of the cortex that are most affected in schizophrenia and in PDP. With respect to the cognition, it's the same thing. So for Parkinson's disease, we used to call it a subcortical dementia. It's a subcortical dementia because it's very different from Alzheimer's or any other type of dementia, which are considered cortical, but memory and behavior are the first symptoms. In PDP, there's more slowness. So the paradigms that Michael shared are very, very relevant for schizophrenia, probably less so for Parkinson's disease. In a nutshell, the proof of concept in schizophrenia, the primary variable would be efficacy with the PANSS total, which is a construct that has positive, negative, and other symptoms, the general symptoms. Then if that study is positive, then you should launch, as typical is a phase 3 program, where you can include in that phase 3 program specific studies on negative symptoms and cognition.
I think we had a question from Laura Chico.
Hi, good morning. Thanks. Laura Chico, Wedbush. I have two questions on the proof of concept schizophrenia study. If you could talk a little bit more about the patient characteristics that are coming in. I guess I'm thinking about background medications. I think you might have mentioned inpatient study, trying to understand what you would want to see on a PANSS score basis. And then actually a question for Dr. Halasa. Your preclinical work, have you investigated any combinations of the KCC2 activators with like risperidone or xanomeline in animal models? I guess I'm curious if you're restoring the EI imbalance, how would you think about the impacts of potential combination effects?
So why don't you address the trial, and Mike, you can talk about combinations.
Okay. As I mentioned earlier, there hasn't been many changes in an acute schizophrenia trial from the ones we were doing in the 90s and 2000s at what have been done with the typical antipsychotics and what Karuna just did in phase 2. So we will look for a typical population for those trials, not an antipsychotics. If there were antipsychotics before, they need to be withdrawn for a period of time commensurate with the half-life, in particular the antipsychotics. And the entry criteria for the PASS is going to be similar that you have been in LB Pharma and Karuna. The only difference that we were considering, and we think we're going to adjust, is to look at the duration of the disease. we might not want to take the oldest of the oldest schizophrenic patients with 25 relapses and 40 years of disease evolution. But other than that, it's going to be the typical acute schizophrenia trial.
Great question. We haven't done any combination medications in animals, but maybe I could say a few things about that may go to the core of your question. Is what is the kind of theoretical framework for KCC2 in schizophrenia, or what's the circuitry that we're thinking about? So, like Oliver mentioned, the dopaminergic kind of idea in schizophrenia is probably downstream of a frontal change in kind of the regime by which the frontal cortex works. Now, traditionally, we've just done D2 blockers. They take care of the positive, voices for the most part. Delusions actually aren't particularly effective because they have a cognitive component to them. Xanomeline trospium went one step above, right, with this cholinergic mechanism, and it has efficacy to work. I mean, I've used it clinically. It works much better for negative and cognitive symptoms than traditional antipsychotics. Now, the promise here, or the idea here, is that you're going even one step above that and going to the source of what I call the blast, the prefrontal deficit. And what I didn't, there's a couple of preclinical data that I didn't show, which would be good to mention here. One is the deficit in KCC2 in the animal models that we have is specific to the prefrontal cortex, right? So we've looked across cortex, hippocampus. Sensory cortex, KCC2 is fine, even in these models. Hippocampus, KCC2 is fine. Another thing that we did, I think that's really relevant, is we've done genetic knockdown of KCC2 in prefrontal cortex and in somatosensory cortex as a comparison. You knock down KCC2 by 50%, you reproduce the schizophrenia-relevant phenotypes. You knock it down in S1, nothing happens. You knock it down in hippocampus, you get seizures. So it's an interesting kind of, maybe that's too much information, but you get what I'm saying. There's a story there about frontal function and schizophrenia that people have thought about for a very long time, and now we have the tools to kind of elucidate that and hopefully reverse it.
And Laura, just to be clear, in psychoses, we haven't trialed two drugs at once. We have, in various forms of very acute seizures, put our drug on top of benzos and things like that, and we've seen the restoration, actually, of excitatory inhibitory balance where a benzo unto itself couldn't do that. But those are seizure models. Miles.
Two questions. One's on KCC2 biology, the other one on the ketamine trial design, actually. So the first one is just, do we know why the glycine transporter inhibitors actually failed in many of the indications you're going after? There's a lot of literature out there supporting glycine and control of KCC2 expression. So I'm wondering why that indirect pathway didn't necessarily work and why your direct activation would. That's the first one. Second one on the ketamine trial design, is the 10-day washout period between the crossover enough? If you look at depression studies, we're having dendritic spine expansions, those sort of things happening months after single doses. And I'm wondering whether you're changing the baseline of your EEGs when you're doing that comparison. Thanks.
So I see Alistair is smiling already. We'll let him take the second one. But in the meantime, since you have a world leader in psychosis translation, I'll let Oliver take question one.
So glycine transporters inhibitors, why did they not work? Well, there could be tons of reasons why they didn't work, of course. Drug didn't get into the brain in enough concentrations. It doesn't hit the target correctly. You need to have glycine there for it to work, etc., etc. But I think actually it's probably not necessarily targeting the mechanism specifically enough. It's boosting NMDA receptors, which may be part of the problem. But actually, these GABAergic markers and the genetics, it's not just NMDA. This is GABA. It's other excitatory pathways as well. So, I don't think the glycine transporter inhibitors may be broad enough to cover all of that.
wash out after ketamine, and we're still debating that. As you mentioned, ketamine could produce changes that outlast the PK of the drug. It's the famous PK/PD dissociation of this type of drug, and that's our concern. That's one of the reasons why we're doing the trial in a site, a bio trial in Newark, New Jersey, where they have done that many times. Okay, so we if you put a gun to my head and it said it's gonna be 10 days, I don't know. I think it's gonna be something like 10 days. It's not gonna be 2 months. It's gonna be something like 1 or 2 weeks, something like that. Closer to 2 weeks than 1.
Frank Briswell with LifeSci Capital. So just a couple here. There's obviously a lot that was discussed. We talked about the importance of kind of the convergence of all the data, a lot of preclinical data. Is there something, though, in there that was extra shocking or surprising from your perspective, or is it really just as a whole and we're not ready to discuss our favorite kid here? Sort of.
So I'll go first, and then maybe Oliver, if you want to speak a second. So I think, what I sort of summed up before, I think matters a lot to us. Unfortunately, giving a rat methamphetamine, which I tease LSAO a lot about, is, well, what can I get out of that? What does that tell me relative to the inherent risk of studying a form of psychosis? But I think you've heard the word converge a lot, and we really mean that, because what we're seeing is essentially the underlying biological changes of neurotransmitters that we want to see across now 25, 30 different disease biology models, which together is giving us great conviction, coupled with the work that Mike showed about rescuing working memory, right, and certain behaviors, and the specificity for KCC2 in these genetic models of schizophrenia. And then finally, being able to hold ourselves up against active doses of reference products and see that in addition to that broad armamentarium of data, that we're affecting the biology as we want to do and the neurotransmitters in a way that should be hopefully restorative relative to some of the worst symptoms of these forms of psychosis in areas like schizophrenia, for example. We now know that we are matching or outperforming drugs that are good drugs and the only drugs that are used. So it's really the totality of that triad together that gives us a lot of conviction. And what we're trying to do before we invest in expensive and large pivotal studies or phase 2 studies is extract as much helpful information from the electrophysiology and these translational biomarkers that we've established in animals to give us conviction about where we put the best expenditure of capital for the next set. So if we're seeing all the things that we hope to see in animals in healthy volunteers and then in this ketamine challenge, gives us incredible conviction to march into that schizophrenia proof of concept study. But Oliver gives you an independent view, which I think is nice to have in addition to company management. So Oliver.
Okay. What I think is interesting here is that you've got a biomarker with QEEG that is measuring electrical activity that, as I said, this is how the brain works. And EI imbalance it disrupts this. So here we've got something that you can measure, as Meg said, across preclinical into clinical. So I think that's the real advantage. And I've been looking for something that is able to change this biology for quite a while. And so, I think this is why this target is interesting.
Thank you. And then just maybe a last one on that is, we talked about the other drugs that are out there right now and issues with tolerability. Do we understand why we cannot overmodulate KCC2 in terms of the safety side?
Yeah, I'll start, and then either Mike or I think Mike would be a good person to answer this. But essentially, energetically, it's almost impossible for this neuron to extrude too much chloride. Do you want to speak to that, Mike?
Yeah. So, this is kind of set by things called electrochemical gradients. So across all cells, there are uneven distribution of ions that you can think of as the batteries driving flow inside and out, and they're balanced by a number of different factors, the concentration gradients and the electrical gradients. You cannot push more negative charge outside of the cell before, the positive ions pull them back. So there's something called inertial potential that kind of governs that, which is kind of the universal reason why action potentials or spikes cannot go above, plus 40 millivolts, because that's it. That's what the battery's limit is. Same thing is true with KCC2. You can't overmodulate it because you can't push out too much chloride. Otherwise, the driving force will push them back in.
Good question. Is that Basma?
Yeah. Hi, good morning. This is Basma on for Mark Goodman from Leerink. We have a couple of questions, please. So the first question is, could you provide some information on the level of the KCC2 activation that you would need for this antipsychotic efficacy, literally in terms of receptor occupancy? And does this level of activation translate well from the animal models to human models? Our second question is about the indication for the first indication you're pursuing for the KCC2. You mentioned that you're pursuing the Parkinson's disease psychosis. Why did you decide to pursue that first before Alzheimer's disease psychosis, for instance? Did you do any animal works in Alzheimer's models, and did you find similar efficacy? And for strategic reason, you decided to start with PTP first. And just to follow up on that, would you expect this mechanism to be generalize and be effective across the different dementia-related psychoses, or this is something still in the work? That's it.
So I'll say 2 words and I'll pass it over to Eliseo, who's given us a lot of thought. One thing, Basma, may make you a little bit frustrated. Eliseo can speak broadly, although some of our receptor occupants and some of the specifics does happen to be a competitive landscape. I'd prefer to not give everything to the rest of the world. But in terms of our strategic decision-making around Alzheimer's psychosis and other forms of psychosis, we think this is a broad syndromic antipsychotic. We think this has broad relevance. Why not march into Alzheimer's psychosis immediately? Well, for a couple of real-world things. Yes, we're continuing to build the armamentarium of evidence around it. We think there's some very translatable things that we could learn from schizophrenia and PD psychosis. And also, when we look at the studies that are being done to assess Alzheimer's psychosis or Alzheimer's agitation, both of which we think KCC2 direct activation is a good target for, to get to a hard answer in terms of a proof of concept is a bigger study and a longer study. So we're very interested in that, and we probably will be talking to you about that if some of these plans go as we have suggested that we think they will. But it's a very big study out of the gate. When we can get more confirmatory electrophysiology, we can start to get a read-through from other forms of psychosis, and then initiate that program when we have the totality of data in our hands that gives us conviction for a longer and, frankly, more capital-intensive trial. Because it's a bigger N size and it takes longer to enroll. But Eliseo, please expound on that.
Yes. On the first one, without sharing competitive information, we have a strong evidence of binding and a strong evidence of activity. So as I mentioned, the EC50 0.6 micromolar, and these are concentrations that we're confident we are achieving. And the electrophysiology that we have seen in animals, it's another piece of the evidence that we're doing. The drug is doing what it's supposed to be doing at the concentration. The only thing I would add to the Alzheimer question is that, of course, all of us has, in addition to schizophrenia and Parkinson, that should be for society, for our families, terribly positive. I will point out, in addition to what Meg said, is that if we have a positive proof of concept in schizophrenia, you might decide to do phase 3 on Alzheimer's disease, as other sponsors are doing. It's a matter of funding.
Next question. Imogen.
From Cantor. Given that we have the world's biology experts here, I do have a biology question. So you talked about the post-mortem findings of downregulation of KCC2. Does direct activation of KCC2 impact expression? And did you find that in preclinical studies? And then as you think about the situation in schizophrenia where patients may have downregulation, how do you expect activation to work?
Great question. Many things I can respond with. First is these post-mortem studies were done with immunohistochemistry. We repeated those using publicly available data sets with single cell RNA-seq, and we find the same thing, that this replicates. So the mRNA is reduced and it's very robust. In the experiment that I meant, so it's reduced. The expression is reduced. Under the conditions that we measure, I don't think that we're increasing the expression of KCC2. We're just activating whatever is remaining. And in the experiment that I mentioned, this came up actually yesterday, is that when we knock down KCC2 by 50%, we can still rescue that with direct OV compounds. So whatever is remaining, we can kind of restore the chloride homeostasis with the direct activation.
Hi, Matt Hershenhorn from Oppenheimer. Thank you so much. Really appreciate this today. The question we had is just, have there been other attempts by academics or other sponsors to develop KCC2, specifically direct activators, and any lessons from those? Meg, I don't know if you could talk a bit about the IP and advantages you see there. And if you don't mind to just reemphasize why the direct activation specifically is the right approach here. And just sort of big picture, as you look to other indications, you referenced your portfolio of other next-gen approaches, presumably with different PK profiles. Just kind of curious how you look across the spectrum of these indications and what, could be more appropriate for either side of that spectrum as you look at the additional indications.
Yeah, very, very thoughtful questions. So I mentioned that direct activation matters because we believe we can see, and we've proven it, when we have a very rigorous set of criteria that any potential development candidate at Ovid goes through for the direct activation portfolio, where we need to see essentially certain clearing criteria that not only have we identified where they bind, but also that we're seeing the output that we want to see, that we're able to actually test for the chloride extrusion. And being able to directly activate that transporter matters, not just in order to achieve the extrusion of chloride that we want to enable GABA to be hyperpolarizing, but it also matters relative to the safety and tolerability profile. Now, for example, if you go out and look in the literature, Matt, you asked the right question, which is, have other people tried to do this? Yes. And it's hard. It's very hard to get to the medicinal chemistry to get into the pockets that we need to directly activate this transporter. It's been very hard for the field. Our team and others have worked tremendously on this. But one of the things we know from the work of others is others have tried to drug the target, but they haven't been able to directly activate the transporter. So they don't get that efficient balance and flow of the ions out of the transporter. They may operate on it in a different way, but they might not have the same, essentially, mechanism of action. And if you go back and you look at, for example, literature on a tool program of another company that's tried to be in this place, you'll see that that's referred to as a potentiator, and I believe that's probably a neuroactive drug. We've screened those backbones and run them head-to-head against our own direct activators, but they operate a little bit differently. They're neuroactive in a different way. Some academics have suggested they operate a little bit more like a GABA PAM. So essentially what I'm saying by that is by not directly activating KCC2, but by modulating the target or hitting the target in an indirect fashion, you may have neuroactivity, but you're not necessarily going to have the same activity that we can through our direct activations, again, through the appropriate flow of those ions and balance of those ions. In terms of our discovery library of KCC2, so this has not been an easy target to crack. It's almost like a KRAS-like target in terms of the challenge from a medicinal chemistry perspective. But we have learned so much about this target in the time that we have been developing 350, the tool program, then 4071, and we have terrific IP on those. So for 4071, we have composition of matter IP into 2046, and we have, I think, you can check me on this with Jeff, but at least 13 other method of use patents, and we'll continue to build upon that portfolio. So very strong, long IP runway. So that's great. But you heard us say we are the KCC2 company, and if our thesis is right about this, we want to have multiple molecules because we believe the therapeutic opportunity is PD-1-like in terms of scope. We think it's incredibly broad. So we have now identified a much more efficient screening criteria for our candidates. We have built new structures or new backbones on 2 series of next-generation chemistry, and it's our ambition and our goal to be able to yield at least 1 new development candidate into the clinic every year for subsequent years going forward, which, of course, is also completely new IP because they're completely unique molecules in new series. I think Ram has a question in the back.
No, I have a question. Hi.
Okay.
Yeah. So Manasa, on behalf of Bob Allen from Roth Capital, so can you confirm if you're developing OV4071 as a monotherapy or as a combination with FOC for PDP and schizophrenia? And if combining with antipsychotics is a possibility, do you have any commercial antipsychotics in mind? And another question is, can you also discuss whether the headache, nausea, and GI side effects are pertaining to in OV350 phase 1 study, it pertains to the molecule and not the KCC2 activation?
Yeah, we'd be happy to answer those questions. So let's start with your question about a monotherapy. Yes, it is our intention to develop OV4071 as a monotherapy for schizophrenia and for the other psychosis indications that we've discussed with you here today. Why? Well, we're highly potent as a monotherapy in psychosis models. So we're seeing incredible activity at very low doses and in really strong safety margins. So it's our intention to take it in as a monotherapy. However, there is no concerns that we have right now based on the potential drug-drug interaction portfolio that Eliseo described earlier that would potentially concern us about potentially exploring combination therapies in the future. And we have trialed combinations in different disease biology models with our KCC2 direct activators. And then in terms of the extremely thoughtful question that you have, so there's nothing that to be clear, that we don't think would prevent it from being used in a polypharmacy regimen based on what we know today. Or future combination therapies, to your point. We think there's a lot of IP and drug potential here. In terms of your question, which is a very good question about our tool program, OV350. So you heard me say earlier, OV350 was actually a great tool program for us to ask and answer some really critical questions about trying to pioneer and drug an entirely new biological target in the brain. But as a development candidate, it had some aspects that were less attractive than what we have with OV4071. So one of the things that we did note, and it was in our slide about tolerability profile, so we saw in our phase 1 study with the tool program OV350 some headache, and we saw some nausea and basically GI disturbance. And looking at that, there was an aspect that we knew about with 350 that made it less attractive for long-term drug development, which was its secondary pharmacology. It hits a secondary target called CCK1. If any of you guys cover the GLP-1s, you'll know you hit that. What does it do? It induces GI motility. So we saw a bit of that with some of the subjects in our phase 1 program. Importantly, one of the aspects that makes OV4071 so attractive is it doesn't have any concerning secondary pharmacology like that. And it looks to be both incredibly well tolerated and, again, very potent. So we don't expect to see the same thing there, but that was one of the things that we knew about going into the phase 1 program, and we saw some signs of that.
Ram Selvaraju from H.C. Wainwright. Thanks for taking my questions. Firstly, with respect to schizophrenia, I was wondering if you could comment on the specific applicability of the PAN-SS as an efficacy endpoint in the acute schizophrenia proof of concept study, and also if you have any plans with 4071 specifically to assess the potential applicability of this compound in a long-acting injectable formulation. Secondly, I was wondering if you could perhaps comment on the applicability of the KCC2 activation paradigm in neurodevelopmental disorders, particularly as this pertains to ADHD and autism. And then lastly, in DLB, since you mentioned it on the slide as one future indication area that you might explore, can you perhaps talk about which kind of route in DLB might be most applicable within the context of KCC2 activation? I mean, historically, we've seen clinically, for example, with zervinosine going down more a neuropsychiatric pathway and an anxiolytic pathway. Conversely, with neflamapimod, we're talking about, assessing activity on the basis of an endpoint like CDR sum of boxes. So which of these paradigms in DLB might be potentially most applicable for KCC2 activation? Thank you.
Thank you. You gave us quite a few, Ram. I'm going to answer one, and I'm going to hand it over to my colleague, Eliseo. In terms of formulation, yes, we are looking at multiple forms of formulation, not just for OV4071, but also for the other candidates that we have in our discovery engine, because we believe, exactly as you're suggesting, that there's multiple ways to serve both acute and chronic potential symptoms of a range of different psychoses. So we're looking to formulate broadly, not just 4071, but also the other candidates in the library. We feel very confident with the strength of the oral program going forward that we've got a very good oral and chronic dose. But that's work that remains ongoing and is certainly a core feature of our strategy. Eliseo, why don't you talk about the endpoint design? Do you want to do that?
Let's start with the last one that I remember and try to go to the So, yes. So we believe one important thing in drug development is not to get ahead of your skis. Okay. So what Meg mentioned is that there are a number of models very relevant for psychotic disorders to active model, single dose, one model, repeated dose, and social interaction, and so on and so forth, is the convergent. Based on that, we believe that there is a strong case for the efficacy of 4071 in psychotic disorders. We plan to study dementia with Lewy body psychosis because there is psychosis, like in Parkinson's disease psychosis. Initially, we would look at the psychotic element, the number of hallucinations, and there are the scales we use in, the SAP and the scales that are used in Parkinson and Lewy body dementia. They come from psychiatry, so there are adjustments from psychiatric scales. The CDR sum of boxes, we might use that as a secondary endpoint. Michael mentioned very interesting data in cognition. It might be that there is an effect on cognition. And the interesting thing of thinking about Alzheimer's disease psychosis or Alzheimer's disease agitation, that would be measuring both. So in the three dementia conditions, dementia with Lewy body, Alzheimer's agitation, Alzheimer's psychosis, we will have a secondary assessment with CDR sum of boxes or some cognitive scale.
I think you're hearing Eliseo and my colleagues say that while we think the opportunity is potentially broad to handle a range of aspects of various forms of diseases, we're trying to be very focused in the endpoints that we go towards psychosis and measuring that to establish proof of concept, right? I think we've had really smart colleagues and peers in the field who have gone after psychiatry, but they've gone very broad. They've had a hard time showing significance across so many different domains. It muddies the water. So you hear us very much focused on the psychiatric scales and honing in on that, though we believe the benefit of KCC2 direct activation may be even broader. We have a question in the middle.
Hi, this is Jenny. I'm online for Tom Schrader at BTIG. Thank you for taking the questions. I have a couple of questions. First, how exciting is a safe clozapine? How exciting is a drug with measurable effects on positive symptoms and no exacerbations of negative symptoms? And secondly, you guys made several KCC2 activators. Are the effects of the activators consistent across models where the less effective activators are consistent, or do they act more like punitive adversarial across models with some successes and some not?
So I'll start, but I think, Oliver, you should weigh in terms of how exciting is a safe and potentially more effective clozapine. I mean, I think you're hearing us, it sounds perhaps hyperbolic, but I mean, we think drugging and directly activating KCC2 could be a PD-1-like moment for the brain, and both in terms of breadth, but in terms of meaningfulness, of potentially being able to address with a completely new mechanism of action that appears, at least in animals, that should be very well tolerated, symptoms of diseases that are just completely unaddressed today. And we know, if you just look out, by 2030, we have essentially a silver tsunami coming. And what I mean by that is all of the baby boomers in the United States will be over the age of 65. So what does that mean? It means we're going to have a lot more psychosis associated with PD, Alzheimer's agitations and delusions, right? And so as our populace ages, effective medicines in these areas that can be used chronically and safe and well tolerated and work with other medicines is incredibly powerful and I would argue much needed. But Oliver, I'll let you answer that question.
Thank you. Well, I would be delighted to have a safe clozapine. I use it an awful lot and it's really tricky to use. But actually, why I'm excited about this mechanism is I think it goes beyond clozapine because it's targeting the EI imbalance that isn't really addressed by clozapine. It's targeting what I think is underlying the negative symptoms and the cognitive impairments as well as the psychosis. I think KCC2 makes sense as a target for that. I'd be delighted if there were any other ways of doing it as well, but I think this goes beyond clozapine if it works.
I think there was another really good question about how did we perform relative to reference drugs. There is not a model that I can think of, and I'm looking at Eliseo to check me, but essentially we're seeing broad activity in these disease biology models, and in several cases our direct activators are working in models that known reference products like pimavanserin doesn't, and we're seeing activity in all the models where we're running head-to-head that's either commensurate or superior to. So, of course, animals are not the same thing as a patient, but the totality of all this across multiple different genetic and stimulant models across now a battery of somewhere between 25 to 30 different PD models is highly consistent. And giving us great excitement. But I think, unfortunately, we're at time. I want to thank you all for the really thoughtful questions and the participation today. We have our subject matter experts in the room, including the independent physicians and clinicians and researchers. So if you have additional questions, I encourage you to speak with them. And thank you again.